enjoying the we're having. Okay. Tonight well, Doug, do you want to give a little quickie on what's going on as far as start parties or anything, or should we talk about that after our speaker?
Doug, let me try unmuting. Okay, we can do that afterwards because there's really not much. So,
all right, very good. Okay, so this evening Jeff got us a great speaker. It's on gravity. Some of us have already attended a previous meeting on that, and I think this will really help to clarify some things that people like myself just don't understand. And I'm really looking forward to this. Jerry, who is a physics professor, probably would be the most knowledgeable about this in our club. So I'm going to have you go ahead and introduce Yannick, and this should be fun.
Okay. First of all, let me say that, yeah, this is the time for everyone to mute themselves if you're not, please. So our topic tonight, as you know, is going to be gravitational waves. And in April, Dusty Madison introduced us to his work in pulsar timing as a method of detecting these. And now pulsar timing is a method that attempts to detect very low frequency waves, and none have been detected using this method yet, but it still looks very promising, and Dusty is still very excited about his work. On the other hand, several high-frequency gravitational wave sources have been detected by LIGO, and that will be the focus of tonight's speaker. Yannick Lecoeuche is a graduate student at the University of British Columbia, where he is part of the Gravitational Wave Astrophysics Group. He has been an operator of the LIGO Hanford Observatory and is now studying how Earth-based noises affect the signals received by LIGO. Besides measuring incredibly short distance, Yannick also enjoys rock climbing and board games. Everyone, please welcome Yannick Lecoeuche.
Hi, everybody. Thanks for the introduction. Yeah, I'm a grad student at UBC. I don't know, well, it sounds like you've had a previous gravitational wave related talk. So hopefully the stuff that I go over, at least at the beginning, is not gonna bore anybody or sound too familiar. So anyways, let me share my screen. All right. Can people see this?
Yes.
And people can hear me okay?
Yes.
Okay.
And now I'll mute myself.
Okay. Also, you know, it's a longish talk, or, you know, there's a lot of slides. So if someone has a question that they'd like to ask, I'll try and keep my eye on the, you know, the Zoom part of the screen, if anyone wants to raise their hand, like during the talk or something, because sometimes it can be hard to remember at the end what your questions were. So feel free to ask questions. All right. So exploring gravitational waves with LIGO. So most of you probably already have this down, but LIGO stands for Laser Interferometer Gravitational Wave Observatory. There are two LIGO observatories. One is in Hanford, Washington, which is like East Washington State, and then the other one's in Livingston, Louisiana. You can see some photos here of the two. They have like the central building and these 4-kilometer arms going in perpendicular directions. Hanford is a desert, and that's the one that I worked at as an operator. And Livingston is, from what I hear, I haven't had the chance to visit, but it's located in a swamp. So they each have their own kind of unique issues that come from those things, but we can get into that later. So in addition to the two LIGO observatories, which are based in the US, there is a much smaller, higher frequency observatory based in Germany called GEO 600. We also collaborate with Virgo, which is based in Italy. There's a observatory that is under construction in Japan called Kagra, and then LIGO is working on all of the like land grants and whatnot to build another location in India. And as we'll kind of go over later, having like many locations spread out is very useful for detecting signals. So these are the people that we work with at this point. And in general, the LIGO scientific collaboration consists of many, many people, I think like 1,000 plus. So it's a big group working on this. All right, starter stuff. Where do gravitational waves come from? They're a result of Einstein's theory of general relativity. So in general relativity, massive objects warp space-time, which we interpret as the force of gravity. There's a quote that I've seen online as being attributed to Douglas Adams, but I'm not actually sure, which is matter tells space how to bend and space tells matter how to move. So, you know, as in this kind of representation we have here on the right, massive objects bend space-time, and that determines how other mass moves in the vicinity of that. And then, of course, have a little picture of Einstein. Have to give credit. Generally, lots of the sources that we see gravitational waves from are extremely massive objects because they warp space-time more, the more mass they have. This being, the more massive objects being suns, neutron stars, and black holes. Neutron stars are left over from the gravitational collapse of a star after a supernova explosion. Black holes are basically neutron stars where the neutron degeneracy pressure has been overcome by so much pressure from all of the mass. So you have these very massive small bodies that light cannot escape from the event horizon. I'm sure everyone's on board with this. You're all space lovers. And then so the question is, if mass warps space-time and you have this, maybe in your mind representation of like a 2D surface and a mass, and it's bending that surface down, then what happens to the surface if you start moving that mass really fast? And the answer is you get these ripples. And so this is what you can think of gravitational waves as being, basically being these ripples in space-time that are created by rapidly accelerating massive bodies. So there's a few definite gravitational wave sources and some suspected ones. The ones that are definite are compact binary coalescences. Those are like black hole mergers, neutron star mergers, basically any two massive bodies spiraling towards each other. Those are the ones that we've detected. We expect to be able to see gravitational waves from supernovas, but there's debate on that because basically we'd only see it if it was an asymmetric explosion. Spherically symmetric movement of mass would actually generate no gravitational waves. So whether or not we do see gravitational waves from a supernova when one occurs will give us some important information about what supernovas actually look like. There's continuous wave sources, which I think relates to the pulsar talk that was given previously. So one such source of continuous gravitational waves could be like a neutron star with that has, say, some kind of deformation on the surface, like something like a mountain, and it's spinning really fast, will create these small levels of gravitational waves, much smaller than like two black holes crashing into each other. But because it's continuous, given enough time, you can extract that signal from the data. And then the last source is mystery source. You never know what you're going to find out there. So LIGO is unfortunately geared very specifically towards compact binary coalescences. So you have to to get a really good sensitivity in that frequency range, you give up your sensitivity in other frequency ranges. So the chances of us detecting something new and out there is kind of limited by our frequency band, but we'll get into that. So here's a pretty good representation of a gravitational wave merger. So I'll just play this video and pause it routinely. This is that same representation we saw of space as being two-dimensional, and the warping of space being this this downward curve below the two black holes. So this is part of the in-spiral phase. At the bottom, at the bottom here we can see the progression of the gravitational wave signal that would be seen by LIGO as this occurs. So as they get closer and closer together, the frequency of their merger starts to increase because they're moving faster and faster, and the amplitude also increases. So there's more gravitational waves being sent out. And then they have this spike as the merger occurs. And then that's followed by this very short ring down where the black hole, the new single black hole, is basically kind of settling down. And then all of this creates these ripples that we had detected at LIGO. Oops. Okay. So I mentioned a little bit about, I guess this is more of a reiteration, but gravitational wave signals as seen by LIGO kind of take this form where during the in-spiral you have relatively consistent frequency going up and down, and then as they get close and close together, the frequency and amplitude increases, and then it spikes as it merges, and then there's this ring down. So one reason that we're interested in gravitational waves, besides just, being a way to confirm the theory of relativity, but just another way to confirm the theory of relativity, is that they are able to pass through all matter. And it makes it a very different way to view space than light. So basically, we're able to detect gravitational waves from any direction. You don't have to worry about like light distortions from light being bent by gravity, or from traveling through some kind of interstellar gas that will absorb some of the light. And so gravitational waves that we see are basically, they're very quiet, but if they're high enough above the noise, they're basically, I don't know if pure is the right word, but there's no warping or anything by any kind of intermediate things in space, because it just travels through all matter. It also allows us to look at things that don't necessarily emit a lot of light, like black holes, which are very obviously like notoriously hard to find using electromagnetic observatories, because they don't emit light. They're obviously, the strongest signals that we see. So it allows us to look at things that has been eluding astronomers for a while. And now that I've talked about the bending of light, I can show this cool animation of two black holes merging, and you can see how the light in the background gets warped during this merger, and just generally bent. And it's I could watch this for a long time. But yeah, I mean, these kind of mergers are, oh, sorry. Okay, so when two gravitational waves merge, as they are passing through space, they stretch and squeeze space in perpendicular directions based on some kind of polarization. So say that you have a circle in space. This is a vastly exaggerated effect, but as a gravitational wave would pass through, you would see this stretching in like in this case, in the horizontal direction, and then go back to normal, and then stretching in the vertical direction, go back to normal, back and forth. And that is this kind of increase in frequency we saw is the frequency of stretching and squeezing in these perpendicular directions. So we also need to do a little bit of interferometry basics. So light interference, light has phase. So, light is basically an oscillating wave. And if you have two oscillating waves that are in phase with each other, you get constructive interference, which gives you a stronger wave. And if you have two oscillating waves that are out of phase with each other, and I guess crucially the same frequency, you get destructive interference and you get no wave. And that's relevant because the structure of an interferometer is like this. Basically, you have a laser, you shoot that laser out to a beam splitter, which basically transmits 50% of the light that hits it and reflects 50% of the light. So you're basically split this beam into two beams that are same frequency, equal amounts of power. They travel down these 4-kilometer arms that we saw that LIGO has. They bounce off mirrors. They come back, and basically the lengths of the arms are such that the laser beams that come back are out of phase. So they're destructively interfering. So when they're recombined at the beam splitter, some fraction of them are going to bounce off back down to this detector here, and some fraction of the ones coming down from the top will transmit through. And basically, nominally, that means that there's going to be no light on this detector at all. So in LIGO's nominal state, everything's dark. Then when a gravitational wave passes through, I mentioned that there's this squeezing and stretching in perpendicular directions. And what that means is that you'll have one arm of the interferometer that is getting squeezed in space and one arm that's getting stretched. So suddenly, somewhat like this at some frequency. And basically what that means is that the arms are no longer going to be destructively interfering, and you end up getting some light at the detector. And the amount of light that you get is completely dependent on, the strength of the signal that's coming in, and also, the frequency at which it's stretching and pulling. So we have a good, very useful animation of this. Here we have, this is our laser, this is our beam splitter. The light is getting split down these two arms and is reflecting back. And at this point, it is in that nominal state where they're destructively interfering. So there's little to no light reaching the detector. And then as the length between the arms changes, you get this very fast, well, they'll go through in more detail, but the length between the arms changes, which allows light on the detector. And they actually, in this video, mimicked the movement of the arms to kind of follow what would happen in an actual gravitational wave signal. So they start moving slowly, and then they build up really fast in this peak. And you can see, yeah, so in this case, they're changing the length of the arms, and you can see that these beams here are no longer destructively interfering. And that's the very basics of how LIGO works. Sorry. Unfortunately, the thing I showed earlier that consists of maybe 5 parts is a little too simple. This is I would say a little bit of an outdated schematic of just the optics in the LIGO system, like the main optics. So there's a lot of this whole section is mostly devoted to making sure that the laser light is at a very specific, like, narrow frequency band, because normal laser light is is relatively, I would say is constrained pretty well in terms of frequency band, but it needs to be really, really well constrained. So this whole section on the left mostly is devoted to making sure that you have like a extremely narrow frequency band beam of light. And then this section of mirrors down here is the signal recycling cavity. I believe it does something pretty similar, but we should come back to that later. Anyways, the main point being there's actually a lot of components that make that LIGO is composed of. So going back to the structure a little bit, this building in the middle is called the corner station. These arms here are called the beam tubes that the laser travels down, and then the mirror that it reflects off of is at the end station, which is 4 kilometers away down in this building here. There's also a mid station, but it's not really used. They used to have a 2 kilometer arm interferometer that was right next to the 4 kilometer one, but they don't really use it anymore because it picks up all of the same ground vibrations as the 4 kilometer. So when there's noise going on, it's not very useful to have. A very important reason that LIGO is so big is that the amount of gravitational wave strain, the amount of stretching and squeezing that you see, the light that comes onto your detector is proportional to the length of your arms. I think it's directly proportional. So if we were to double the length of these arms to 8 kilometers, then we would see not twice the amount of gravitational waves necessarily, but we'd have double the sensitivity. So that's why they're both are built in these places where there's enough space to have basically 4 square kilometers, and they also have to be far out enough that there's not that much noise. So that's why this is out in the desert. Livingston's in a swamp, not too many people driving around or doing construction or any of that. One interesting thing in LIGO is that in addition to the arm length being directly proportional to the amount of gravitational waves you can see, the stronger your laser is also, or the strength of your laser is also very important. So the stronger your laser light is, then when there is this very minor shift in the phases between the 2 arms, that means you get more light on the detector, which means you have a higher chance of seeing a very weak signal if your laser is very strong. So in order to keep as much light in the arms as possible, they use pure fused silica mirrors. They're extremely reflective. They absorb just 1 in 3 million photons. And they're also extremely expensive. They also serve to refocus the beams because, as it turns out, basically laser beams, they diverge over time, or over distance, I suppose. So if you are shooting a beam really far, it's always going to start to spread out. And then so basically the end mirrors help refocus it as it comes back towards the corner station. It's worth noting that even though it's extremely reflective and absorbs 1 in 3 million photons, the laser power is hot enough that that there's actually a noticeable temperature change on the optic from the beam hitting it. So that actually creates this dimpling effect at the center that LIGO fixes, because if you have any kind of temperature change on your optic, it's going to change the focus of the optic. So they use a ring laser to warm the outside of it so that it matches the center, so that you can keep it at the curvature that you want. LIGO also operates in a vacuum. This is because air particles can interfere with the laser. We're talking about really small changes in light between the arms. So basically any kind of air particles are going to introduce a ton of noise. There's also a secondary effect, which is that if there's some kind of dust or something and it lands on one of the optics, the laser will light it on fire and will end up burning a hole into the optic, rendering it useless. So basically the entirety of the 4-kilometer arms and all of these chambers that you can kind of see in this photo at the center are kept under vacuum. It's extremely high vacuum. It's 1 trillionth of the air pressure at sea level. And I believe we have the title of second largest vacuum enclosure in the world behind CERN. And so, yeah, there's a lot of precautions that are involved with this. In particular, you have to make everything stainless steel because any kind of like paints or anything in vacuum, especially in high vacuum, will vaporize. And that just adds particles to your system that you then have to deal with. Let me get to the... So, as I mentioned, the beam tubes are also under vacuum. And because high vacuum is there's so much of a pressure difference, it's actually a continuously spiral welded beam tube for the entire 4 kilometers. It's one weld going all the way through. In order to make it vacuum ready, they heat the tubes. So the entire, these huge systems are heated to 160 degrees Celsius for 30 days. Basically, the heat's supposed to drive out any residual particles that are left in the arms or in the chambers. And then you turn on turbo pumps to pump out a lot of it. And then you have, I think there's supposed to be commas here, turbo ion nitrogen pump vacuums. So I think ion pumps basically have it's passive. So once the turbo pumps that are trying to vacuum out the system do as much as they can, you basically still have a couple oxygen particles bouncing around. And the ion pump is basically just like a highly charged surface that will attract any other highly charged particles that are bouncing around that stick to it. The nitrogen pump is very similar. It's just like a very cold surface. So you have air bouncing around the chamber. Eventually, it makes its way to this basically sheet of ice, and then it gets stuck to it. And so that's how they vacuum out the rest of the air. The beam clothes or the beam tubes after, they're vacuumed and everything, like it doesn't exist as the steel tube here. It is in fact enclosed by concrete and it turns out to be a really good thing. As you can see on this picture on the bottom right, LIGO, it's in Hanford, so it's by the Hanford nuclear site, and it's built on Department of Energy land. So the story is, as I understand it, that the Department of Energy was doing like a desert rescue practice operation where they drive around in the desert, kind of simulating like someone had gotten lost in the desert and they're trying to find them. And you can kind of see that there's this hill on the left side of the beam tube that maybe obscures it a little, and someone just rammed straight into it. So I think everyone was really happy that the concrete was there, because that would have been catastrophic. And the person was okay. So everyone made it out fine, but good to protect your equipment. So one of the most important things at LIGO is isolating your mirrors from terrestrial noise. So, there's the mirror at the center, the beam splitter that I mentioned, and then there's mirrors at the end stations, to make it so that ground vibrations don't come into the equation. You basically have these, I showed you previously, actually, these kind of modules here that are kept under vacuum. Those are placed onto these ISIs, which are inertial seismic isolators, I think they're called. And they're basically these active isolators that measure ground motion and try and move to counter it. So they're on top of these. And then inside of the chamber, you have these 4-stage pendulums that where basically each stage adds another layer of dampening from outside vibrations. If you were to measure the vibrations at the top of the pendulum compared to the bottom, they'd be reduced by 100 million times. That is, of course, dependent on what the frequency of vibrations is, but that's the figure people usually use. They're also suspended from these fused silica fibers, which are made of glass. Well, fused silica, yeah. And they're pulled on site. And basically they're used because they have resonant frequencies that are outside of LIGO's kind of ideal range of frequencies that they're interested in looking at. So there's a lot of work put into isolating things from outside noises, but even so, there's still a lot of sources. So it's a very sensitive detector. Speaking of which, how sensitive is the detector? I believe for the first measurement of gravitational waves, the figure that was used was that they were measuring lengths, within these 4-kilometer arms, they're measuring lengths that are 1/1000th the width of a proton. So really, really small changes in, the stretching and squeezing of space from these gravitational waves. They're exceedingly small. So if you're ever wondering, like, if we're getting gravitational waves passing through us all the time, how come we don't notice? It's because it's extremely hard to detect. And so, like, as I mentioned, on the right here, we have a frequency on the x-axis and basically a measure of the sensitivity on the y-axis. So these lines indicate the noise curves at LIGO. So at a given time, any gravitational wave signal that comes above these lines is something that you're going to detect most likely. And you can see that we have this little dip, this optimal frequency range, and we've purposely optimized it to look for merging black holes and neutron stars. These 01, 02, 03, 04, 05s are the names of the observing runs. So LIGO basically will do an observing run for like a year. It'll take a break, do a bunch of upgrades, come back and do another observing run for a year. So you can see that the line for each subsequent run kind of gets lower and lower as we make the detector more sensitive. So we just finished 03, and 04 is supposed to start in, I think, March-ish. So we have, great hopes for the future. So now we can talk a bit about the first gravitational wave detection, 150914, which is just 2015, September 14th, I believe. It's the combination of a 36 solar mass and a 26 solar mass black hole, which ended up forming a 62 solar mass black hole. And if you're doing the math and it's not adding up, that's because 3 solar masses of that of the 2 what ended up being radiated as gravitational waves. And so that's kind of another way that you can verify the existence of gravitational waves is by looking at the masses before and after these mergers. So on the right in the figure, we have what the LIGO Hanford data looks like. Below it, these thinner lines are the gravitational wave signal templates that were found to most closely match the data. You can see what it looks like at Livingston, which is the other detector, and then they line them up, and you can kind of see, well, hopefully you can see by eye that there appears to be this correlation, but they also use algorithms and stuff, so you don't have to just base it on that. LIGO also had the first binary neutron star detection. So that's 2 neutron stars with masses between 1.17 and 1.6 solar masses. They combine to form a 2.74 solar mass black hole. It happened 130 million light years away, and it also marked the beginning of multi-messenger astronomy, which is really an exciting thing, which is the ability to measure gravitational or astronomical events using both gravitational waves and electromagnetic waves, because basically up until 2015, when LIGO detected the first gravitational waves, all astronomy has been done using electromagnetic waves. And so it's basically like getting a whole new sense to explore space with. And we'll talk a little bit about the things that you can do with that information. But for now, for 170817, we have this video here that basically shows simultaneous gravitational wave strain and gamma ray measurements from Fermi at this, and you can kind of see how they line up. So this is, I guess, this might be useful. This plot has time on the x-axis. It's got frequency on the y-axis, and then the color that you see in the plot corresponds to the signal to noise ratio. So basically you have like the gravitational wave signal starts at this low frequency we talked about. It gets faster and faster as they get closer together, and then it has this peak when they merge together. And then 2 seconds later, they saw this gamma ray burst from, with Fermi. And so that was extremely exciting. They also had some other visual cues that I think we'll get into in a second, that basically show that these are the same event. So one really quick point is that you may have noticed from that plot showing all of the different gravitational wave observatories that they're relatively far apart from each other. One reason for that is that the local vibrations will be different. So say there's an earthquake at Hanford, it's right by, it's in the Pacific Northwest. So it's by the Ring of Fire. And so it gets a bunch of noise. How would you be able to tell that from a gravitational wave? And the answer is that you have multiple observatories in different places. So Livingston is pretty far away, and then there's Virgo in Italy, and you can differentiate gravitational waves from local noise by basically saying we would see gravitational waves like coherent waves between all three detectors, and all noise or most noise should be not coherent with each other between the detectors. So that's one really important reason. Another reason is that LIGO acts as a microphone, which is that if you have a single interferometer and you have gravitational waves passing through, you actually don't have an idea of where it comes from, and you don't get an indication from just the one detector. So what they do is you basically have a few detectors located around the world, and you can look at the time difference between when they see the signal to triangulate where it came from. So in general, having more detectors will mean more accurate triangulation of gravitational wave signals in the future. And we can see an example of this. So this is for 170817, which was that first binary neutron star merger that we talked about recently. And this plot here is a sky map. And it's basically, you get to see with the combination of electromagnetic observatories and LIGO, you see an idea of how well the event was constrained on the sky. So using just IPN Fermi integral, you get this band. And so you say, this binary neutron star merger, it's somewhere in this band. Not super helpful, but good. Fermi GBN narrows it down to this area here. And then the LIGO detectors, as they're detecting it, localized it to this kind of green band, but also this lighter green band over here. And so with the combination of the three gravitational wave detectors, the two LIGO detectors in Virgo, you get this smaller single space for which you can basically tell electromagnetic observatories, look in this spot to see if there's a binary neutron star merger happening. So it's extremely useful. And because LIGO can see the in-spiral parts, as the neutron stars are merging in, which can take several minutes, it gives a chance to basically warn electromagnetic observatories before the actual merger happens to look in this area. Right, and then on the right here, we basically see at the bottom, 20.5 days prior to the event. This is basically the area where they believe it happened. And there's it's in the negative. So things that are extra dark are actually like very bright events, and there's nothing in this area. And then 10.9 hours after the event, when LIGO had told these observatories to look at the spot, you see that there's this new light source. So LIGO has actually detected a lot, I believe approximately 90 gravitational wave candidates in its time. And this is one representation of seeing them, of looking at them. Basically, you have these blue dots. Each two blue dots are the two masses that then merged into this larger dot. And the solar masses are shown on this y-axis. So you see we've had some very large mass black hole mergers, as well as some neutron stars here at the bottom that have merged into black holes. And then you can kind of get an idea from the red and the yellow. These are black holes and neutron stars that were detected using electromagnetic wave observatories. As you can tell, black holes are much harder to find. Neutron stars are much easier to find because they actually emit light. The rate during the last observing run, the estimated rate of binary neutron star mergers is 80 to 110 per cubic gigaparsec per year. And binary black hole mergers, it's 15 to 38. I believe the reason that we see many more black hole mergers than neutron star mergers is basically just because they're so massive, the signals are much stronger. But we can talk a bit about that as well. So in this, we can see, basically, I mentioned that 01, 02, 03 are the different observation runs that LIGO has done. And you can see how this is the number of detections as time goes on throughout the runs. And this is kind of showing you how much the detector sensitivity has improved during all of these upgrade phases. And so at this point, this says 67, so it's actually a little bit dated because it doesn't go to the end of 03B. But yeah, between each run, the detectors are upgraded. It improves both the sensitivity of the detector and the duty cycle. So basically, you want to have the detector operational as much as possible. The duty cycle during this most recent observing run was approximately 51%, and that's for 3 detectors. So LIGO, both LIGO sites and Virgo running, were all observing 51% of the time, which was extremely good. And then with all of this information, you can start to do some real science, looking at different population theories. So in this case, we have the astrophysical occurrence rates. So this is how often you would expect binary mergers with this mass to occur, volume, per year per some amount of volume. And what's interesting about this is we're starting to get enough detections, or like a large enough quantity that you can do statistics, right? So you can say we have all of these mass distributions, and they all correlate to different theories about black holes and their formation processes. And there's something called the pair instability mass gap, which is basically when you have 2 orbiting bodies that are accreting more and more mass, it's possible for one of them to be massive enough that it explodes and knocks the other one away. And that would be like, so things that black holes in that mass range, you would expect to see less mergers because they've blown their counterpart away. And so we can use all of this data to basically start to determine real things about how black holes are formed, what the rates are, and that kind of thing. If we go back to 170817, which was the binary neutron star merger, this actually had a lot of really interesting scientific contributions. So for starters, I mentioned that there was the gamma ray burst that occurred while it happened, and gamma ray bursts were actually a pretty mysterious thing where scientists don't know where they all come from. And so this was at least one part of the answer, where LIGO detects a binary neutron star merger, and then we get a gamma ray burst at a very coincident time. So they think that's at least where some of them come from. Also, the fact that the black hole that would have resulted from the merger is 2.7 solar masses would mean the discovery of a new class of black hole. So if you look at the spectra, if we, so actually, let me go back real quick. These two images that they took before and after the neutron star merger happened, they took the spectra before and after. And from that, you can basically see what elements were present before the merger and after the merger. And using that, they're able to get some really good evidence for making heavier elements, basically being formed by these very chaotic neutron star mergers. So we have this periodic table here, and the merging neutron stars, these bright yellow ones, they basically saw a lot of these elements within the debris and the dust after the binary neutron star merger. And before, they only had theories as to how these were formed. So it actually gave some really important information as to how heavier elements are formed in the universe, because just dying stars and supernovas and whatnot only take you so far through the periodic table. So that was a really interesting event. Another important thing using gravitational waves and electromagnetic waves is you can start to determine the neutron star state of matter. Much like our own star, using electromagnetic waves, you can only see what's coming from the outside. You don't really know what's happening on the inside, and you want to know because it tells you a lot about, how physics works in really dense, hot environments. And so by being able to see it with electromagnetic waves and gravitational waves at the same time, you are able to, maybe not now, but with enough of these measurements, kind of get information about what the inside of the neutron star must look like. And a big component of that is actually figuring out what the radius of the neutron stars are. And that's hard to do with electromagnetic light, but a little bit easier to do using gravitational waves. So this should be interesting. I unfortunately can't tell you too much about quark gluon plasmas. It's not my specialty, but it does seem interesting. Another important contribution it had was helping to measure the Hubble constant. So Hubble constant is the expansion rate of the universe, and what its actual value is tells you a lot about the amount of baryonic matter, dark energy, and dark matter in the universe. And that tells you a lot about the initial conditions, right? What things were like during the Big Bang. So there were two projects, really large projects that used electromagnetic waves. What are they called? Oh yeah, Planck and Shoes, that basically tried to constrain the Hubble constant, and they got two different answers. So you can see that they have these solid lines, which are their guesses for the Hubble constant, plus the transparent lines around them give you like some amount of standard deviation. And they had these two different answers, and then LIGO, by looking at these gravitational wave signals, was able to give a third answer that was independent, that ends up being right in between the two. So this is the probability distribution that LIGO got for what the Hubble constant might be. So they're all somewhat agreeing, which is good, I suppose. But I don't think you'll get a straight answer on who's wrong in this equation. But yeah, so that was a really interesting development. And as we get more binary neutron star measurements and binary black hole measurements, we should be able to constrain it even more. So for the future of gravitational wave astronomy, there's more work to be done. Neutron star state of matter. I talked about supernova detections. With LIGO's current sensitivity, it's really expected that we would only be able to detect supernovas from within our galaxy, and those occur about one every 100 years. So the chances of us being and observing, not in an upgrade phase, and seeing it is pretty low, but it would be very interesting. There's the continuous wave sources I mentioned. There's also this project called LISA, It's what's shown here in the picture. It's a laser interferometer space antenna that it's being run by the European Space Agency. Basically, it's like LIGO, except you have, I think they're like millions of kilometers apart. So that thing I mentioned about arm length being really important is really amplified. They also don't have all of these sources of terrestrial noise, right? Because they're just floating in space. So this is a really exciting project. I can't remember when it's supposed to be, because it keeps getting pushed back like all space projects. So I think it's like 2050 or something now, but that's really exciting. And then in the far future, there's this really interesting phenomena where early in the universe during the Big Bang, or after the Big Bang, while the universe was really dense and hot, it's basically opaque to light or to electromagnetic radiation until, I can't remember the exact amount of time, but like I think at least a few thousand years after the Big Bang. And that means that we can only see so far back into the past to the cosmic microwave background, right? Using electromagnetic light. And gravitational waves are not constrained by that. So if we get extremely, extremely sensitive detectors, you could potentially see gravitational waves from much earlier, much closer to the Big Bang, like seconds after, I think, or fractions of seconds after. So that's something that would be way, way in the future, but an exciting idea. Now I can talk a little bit about being an operator. As an operator, half your time is basically as a technician, and then the other half is you're actually doing the operating, which is making sure that the interferometer stays aligned because it has all of those optics we showed you before, and they're very sensitive and they can become misaligned sometimes. You spend time in this room, which is the control room. This is a nice pre-COVID photo of the control room. But you have all of these screens that basically give you different readings of like how the interferometer is doing and also different potential noise sources. So these screens on the right show seismic levels that you can use to look at earthquakes. It's that's actually a really big issue. If you have a magnitude 6 or higher earthquake anywhere in the world, it's very likely going to knock LIGO out of alignment, and then realigning takes an hour or more. So we do have to watch out for those things. And it's also a 24/7 job. So we had 9 operators and there had to be someone working it 24/7. So sometimes you work midnight to 8 a.m., 8 a.m. to 4 or 4 to midnight. And yeah, so basically what I'm talking about with locking and relocking the IFO is basically all of these mirrors are being controlled by servos to be these perfect lengths apart so that there's destructive interference of the beams. And then, and they're being held there using these feedback loops. And if there's a noise spike of some sort, like an earthquake or something like that, you end up getting, the feedback loops get overwhelmed and then it becomes unlocked. And it's like it's a long process to relock. It takes about an hour, but it's mostly automated, which is helpful. And you want to keep all 3 detectors locked as much as possible. So what we have at the bottom here is basically for a random day during the observing cycle, you can see when each of these 3 observatories has a solid bar, that means it's observing. And when it's a small line, that means it's not observing. And then you can see like this here just shows you like how long all 3 observatories are running, how long 2 were running, how long 1 was running, and how much of the day none of them were running. On the technical side, when I wasn't operating, I worked on the photon calibrator. And the idea for that is basically you have this big interferometer, you spent millions of dollars on it, and you want to know if it works, but you're not sure when or if you're going to see gravitational waves. So what you want to do is you basically want to very slightly change the length in the arms to simulate a gravitational wave. So what the project basically does is you have a laser that you bounce off of one of the mirrors at the end, the end of the arm. The photon radiation pressure will very slightly move it, and you can modulate the beam to basically simulate a gravitational wave signal. So the work I did was basically keeping those calibrated, because that ends up keeping the interferometer calibrated so that when you get a real signal, you understand what the actual distance that space is being stretched and squeezed by is. So that was an interesting project to be a part of. This is me working in the vacuum chambers. As I said, any particles that are left in there tend to vaporize when it goes under vacuum. So you have to be in these clean suits like I'm wearing. My current research is based on this terrestrial noise that we talk about when the noise is transient, like it passes. It's not constant. It's there for a second and goes away. We call them glitches. They occur pretty frequently. The good news is that, like I said, when you get a glitch, when you get some noise, it'll only happen in one of the detectors, and you can use that to figure out what's a noise and what's noise and what's a real gravitational wave signal. The problem being, if they interfere with each other, if they're really close to each other in time, it can actually affect the information you get from that signal. So here we have a real signal, and then this is a glitch, and you can see they look pretty similar. So if you're a detection algorithm that was looking for gravitational waves, you might get kind of confused here. So what I do in my project is I basically inject gravitational wave signals at various points in time relative to this glitch, like is being shown here. And then at each point, each frame of this little movie you're seeing, we run parameter estimation, basically see like where in the sky does the algorithm think the gravitational wave signal is coming from? What does it think the masses are? And then from that, you get these posterior distributions. And so basically this is at each point of interaction that we're seeing at the bottom here, we are calculating what the mass of one of the inspiraling bodies is. And you can see that this dotted red line is the actual mass. In these areas where the glitch and the signal are not interacting, it stays pretty aligned. And then during this point of interaction, it jumps up. And so all of a sudden it's guessing that the masses are, 160, 180 solar mass instead of 80 solar mass. So it makes a big difference if there's some kind of coincident glitch. The reason that we're interested in this is that you could end up having a glitch overlapping a real signal that says that ends up saying that maybe two masses that are neutron star sized, it changes it to say that they're actually black hole sized. So electromagnetic observatories don't have to look at it because we guessed that it was a black hole. And if we find out we're wrong, we'll be really sad we missed that opportunity, right? Additionally, it can change the sky position. So you can get this signal and you can tell a bunch of observatories, go look at this point in the sky. And then because there was this glitch near in time, it ends up being at the wrong spot. And that wastes a lot of observatory resources for other observatories. Additionally, basically because the sensitivity is always increasing, the rate of gravitational waves we see is always increasing. And along with it, we tend to get more glitches because there's a lot of noise that's just below our sensitivity that gets exposed when we increase the sensitivity of the detector. So that's what my current research is on. And that basically concludes. I have a couple like fun slides at the end. I don't know if anyone here has been to East Washington before. Okay, I see one hand. It's a pretty nice place. It's a desert, but one thing is it gets a lot of tumbleweeds. So you may have seen this in the news in the last year or two, where cars were getting trapped under a bunch of tumbleweeds and they had to flush them out. There was also this tumbleweed tornado that was in Hanford County, Benton County, which is just wild. And as you kind of saw from the photos, it's a flat desert, and the LIGO concrete tubes are basically walls in that desert, which means that when the tumbleweeds are flowing across, it ends up catching a lot of them, which looks like this. So normally there's a road, a couple, maybe 6-7 feet underneath here, that leads from the corner station over here to the end stations. And this is the beam tube that we were talking about. And it just gets covered in tumbleweeds, and then we're left to deal with them. One issue that makes this more difficult is that I mentioned we're by the Hanford nuclear site. And so I don't think they had very great waste disposal practices back in the 40s. So what that means is that LIGO's tumbleweeds are also slightly radioactive, so you're not allowed to take them off site. So they end up burning them on site in these big fires like you can see here. And sometimes, I don't know, if it's been raining a lot, you have to like mulch them, and then they like built this custom mulcher that sprays it all off to the side, like on the hillside. But yeah, those were the fun little tumbleweed attack slides I had. But that's the talk. Thank you very much for listening.
Thank you.
Yes, thank you very much. Yes, quite awesome. Love the tumbleweed tornado. Do we have any questions?
I've got a question.
Go ahead, Doug.
Yeah, go ahead.
All right, so I've heard before there's something about the gravity waves are polarized.
That's correct. Yeah.
Okay. Can you explain? I mean, in an electromagnetic wave, I can kind of sort of understand, but in the magnetic wave, the gravitational wave, how does the other dimension, the z-axis work, I should say?
Yeah. Okay. So basically, you have a wave that's traveling. So one axis is you have the wave that's just traveling through space, right?
Right. Your xy.
Yeah. And then so the wave front, let's say, as it's traveling through,
Right.
Say like the plane that wavefront is on, the polarization refers to like that stretching and squeezing I was talking about. So like, let me find the right slide. So like this, right?
Right.
So the polarization basically refers to like, it's got these two axes that it's stretching and squeezing on, and the polarization refers to like what the rotation of that is.
Okay. So it's rotating as it's going through. It's going in a direction.
Yeah.
Let's say it's going in the X direction. The squeezing and elongation would be in the XY direction, would it not?
YZ.
Okay, so it's going.
Wait, which? Yeah, sorry. Which direction is it traveling in this
X
case?
direction. If it's going in the X direction,
If
X
it's going
positive direction.
Yes, then the stretching and squeezing is in the YZ direction.
Oh.
So it's perpendicular to that. Yeah.
Okay. Now
And then yeah. And so that's actually important because I played this little animation here. Oh, sorry. But this is ideal, if it's stretching and squeezing along this axis as the polarization matches up, then you're going to see gravitational waves. If it was at 45 degrees, then it would be stretching and squeezing equally in both arms and you wouldn't see anything.
Okay, so with Hanford and Livingston.
Yeah.
Okay, obviously Earth isn't flat, but they're not that far apart. How much of a degrees off are they? And rather than having it on, on 90 degrees from one from the other, where you're basically got a good separation in the X plane, or XY plane. You only have a small one. Italy gives you a nice other direction, I'm assuming.
Yeah, they're slightly off from each other in terms of their angle, like the
Right.
perpendicular angle. So they should be able to collectively get most gravitational waves. I think Virgo, the third observatory, which is in Italy, is also off a bit from the other two.
That's what I'm saying. Is Italy is going to be very much off from the other two. It's basically going to be like on the Z plane.
Yeah.
But Hanford and Livingston just don't seem to be that far apart to give you that much difference.
Yeah, I mean, in terms of, oh, sorry, what?
And obviously there must be enough, but
yeah. So the distance definitely helps to give you different vibrations like that. That it's definitely far enough apart that you shouldn't have any kind of shared seismic
Right,
noise.
right, but I'm not talking about that. I'm talking about.
You're talking about like the
orientation.
amount of time from hitting one to hitting the next.
That and the orientation.
I see. Well, the
Because Earth
orientation doesn't
isn't-
matter.
Assuming the Earth isn't flat.
Yeah.
So you have a slightly different XY orientation,
Uh-huh.
but it doesn't seem like it'd be that much is what I'm saying.
Okay, so assuming the Earth is flat.
You would have zero. You would
Yeah,
have
yeah.
zero.
Okay.
We don't
so,
have zero. You know.
Yeah. So, but I mean, basically, like in terms of orientation, it's basically like these would be aligned with each other. These
Okay.
would be off axis with each other,
Right.
right? And so it doesn't really matter how far apart they are for that,
Right.
because basically the polarization will be 100% for this and like 0% for this, right? Well, yeah. As for the time, I think it takes about a millisecond
Okay.
time difference between, or like maximum a millisecond time difference.
Okay.
So if it were to travel, I guess you would call it perpendicular to the flat United States, like from left to right or something, it would take about a millisecond.
Right. But,
And that's enough. There's enough, we record with enough resolution that is a sizable amount.
right. There's one more thing in that slide you were showing, and I didn't get the last two digits. The black hole, first black hole merger, 1509, and whatever it was.
Let me find that one. There you go.
There you go. 36 and 26 do add up to 62.
Oh, you're right. Wow, that's embarrassing. Okay. Well,
I did it because I want you to change your thing.
Thank you. That's an extremely good point. Thank you very much.
I can't do the math, so.
No, but on the next slide, they don't add up.
For this one, yeah. I think in this case, it's also it's a range.
Right.
So it's not a concrete mass for the two bodies.
Right. Like I said, I didn't want to do a gotcha, but I just.
No, that was a good gotcha.
Slide.
This is, yeah. I must have thrown this together a little too fast.
I've done those things, so yeah.
Okay.
I've been on your side of it, so.
Okay, that makes me feel better. Yeah.
All right.
Yannick, my question is, so the gravitational waves are actually causing a change in physical distance between the corner station and the end station.
That is correct.
So the
yes.
crust of the Earth is being stretched or squeezed, or the steel tube, or
it's like the space between. It's space itself. So I guess you could say that all along that axis that's being squeezed, all of the atoms and everything are getting moved closer together. But I don't know if it's squeezing in the conventional sense that we think about it. So it's I don't think it's anything that would cause like any kind of reaction between different components getting squeezed. It's actually just the space itself is moving closer together.
Mm-hmm. And then you'd mentioned that, like in this slide here, it shows that this event here was 130 million light years away, but that distance is being measured by gravitational wave measurements or by electromagnetic telescope.
That's a good question. I'm not 100% certain how well those two measurements agree. I believe that the number I got is from gravitational wave measurements.
Because do you know how fast gravitational waves move, or does it depend on the intensity of the
in theory,
event?
They move at the speed of light. But people do look for little differences, like we talked. Oh, stop my video. This one where it shows this gamma ray burst that happens approximately 2 seconds after the peak of the gravitational wave signal. A lot of people were looking at that as some kind of proof that gravitational waves actually don't move as fast as the speed of light, or that we live in some kind of weird warped space where light and gravitational waves have to travel different paths to get to the same spot. But really, there's not that much evidence for all of that. In theory, gravitational waves should travel at the speed of light.
I thought light travels slightly different speeds in different masses.
That's true. In a vacuum, they should travel at the same speed.
Right. Well, then between here and there isn't actually a true vacuum. So
Yeah, I suppose so. So light,
small. I mean, it's going to be small, but there's going to be some variance.
it could be that. I'm not entirely sure as to what the accepted explanation is for that.
Okay.
But people will take any kind of minor deviation as an excuse to write a paper about the 5-dimensional universe or whatever.
Right.
Are the gravitational waves subject to gravitational lensing by objects?
No, I don't think so. I believe they should just pass through all matter without any kind of lensing or anything, which is one reason that they're especially interesting to look at, because you could get them from behind the sun or something, and reasonably expect to believe the signal.
Thank you.
All right. I have a fundamental question about gravitational waves, and that is the restoring force. Does that come from the tension in the space-time? Just in space-time?
That's a good question that I don't think I can give you a very satisfying answer to, because it's been a little bit since my last gravitational wave class. Unfortunately, the specific thing I do is more related to data analysis of the of the detector and the glitches and whatnot. But that is a good question that I'm not entirely certain about.
Yeah, I couldn't find anything on the
From a quick Google
online.
search.
I looked earlier for that.
Yeah.
There's no reference to it at all.
I'll have to
Because
think
it's
about
almost,
that.
there was this thing before Einstein developed relativity, the idea that there was this ether
Right.
that light had to move through, and this ether provided the restoring force for light waves. But we kind of saw that light waves provide their own restoring force, so we didn't need the ether. But this is kind of going back to that the time and space are stiff in some regard and want to be in a certain condition, and that's the restoring force here. But
yeah, I think that is basically the case. But when you get into the math of space-time, it becomes like not a perfect analogy to an actual ether.
Okay. Yeah, I also saw that there's talk of not calling the speed of light anymore. It's just c, the speed of all massless objects and phenomena. So gravitational waves and light move at the same speed, and they're just going to call it c rather than.
I see. That makes sense.
Yeah.
I hadn't heard of that. That's very interesting. It'd be more accurate, definitely.
Yes.
Actually,
can I say something, Jerry? When you talked about a restorative force, the universe is constantly expanding. So how does that, is that what you're kind of getting at?
No, when you have an oscillation, when you have a mass on a spring, when you pull the mass down, the restoring force is provided by the spring. And then gravity pulls it back down. So you have this restoring force that keeps the oscillation going. All oscillations need some type of restoring force. And with light, I'm not going to go into that, but it's not clear what when you cause a ripple in space-time, what's the restoring force that propagates that wave? That's not clear.
Yeah.
Yeah, I'd have to get
It's
back
a
to
distortion. Yeah.
When you throw a rock in a pond, what is it?
Oh, the surface tension of the water.
So at the very end of his one video right after the merger, there was like that peak where the final gravity well dips and peaks down. Could that be maybe the restoring force that you're talking about?
Let me see if I can find. Sorry, was it this one?
Yeah, that was it.
Yeah, I mean, I think in this case, yeah, you're correct that for, if we're using the ripple analogy, then for some surface that is experiencing ripples, and that after being disturbed goes back to a flat state, there has to be some sort of tension. And I would imagine that is the tension of space, though I would not encourage you to quote me on that.
Okay. Fair enough.
Well,
But that distortion is from mass. So when it's not distorted anymore, it has to be from a lack of mass. I mean, that's what Einstein said, that distortion in space-time is caused from a mass.
Oh, it's still
That's
distorted.
what gravity is. It's a curvature in space-time. So if it's being distorted and then it's not, it has to do something with the fact that there's not mass there, that same level of mass.
It's still distorted. It's just not changing.
Yeah, it's not accelerating. And the acceleration is what causes the ripples.
Well, the distortions aren't moving. Distortions becomes static in one spot.
Right.
Right, yeah. And I believe
So
if
is that
it's,
dark energy then? Dark energy?
I don't think so. I think that's
Dark matter?
I think that's unrelated. I believe, so you mentioned the expanding universe, right?
Yeah.
And I think that's that is, it's an important factor. It comes into our calculations a lot, like the expansion of the universe, but I don't think that it is what is providing the tension. I think that if the universe were not expanding and were, say, completely
Static.
yeah, completely static, you would still see these types of gravitational waves. So the restoring force is something
Separate.
more like fundamental.
Can you go to the slide with the neutron star? I got a question about neutron stars, because I've
Sure.
seen that they are extremely magnetic, and my older version of a neutron star is just solidly packed neutrons. But yours was different. Yours had shells with the gluon Clark
Yeah,
plasma. Okay. Now with this model, I can see where if it's spinning, it would act as a dynamo. If you've got neutron proton, you have positive forces in the center, and you've got ions, electrons on the outer shell, that would act as a dynamo, creating a huge magnetic force. Is that my understanding of that correct?
yeah, I believe so.
Yeah. Crazy
Okay.
magnetic fields.
Yeah,
Yeah, and I said before, and I always seen the models were always just, they talked about neutrons. How can a ball of neutrons
just like a
create
uniform
any
ball of
magnetic?
neutrons.
Yeah, because it's uniform. There's no, but this is a different model of a neutron star, quote unquote.
Yeah, I
Yeah.
don't know. This I'm not sure how recent this one is, but it is something that there's,
It must be very recent.
yeah, I mean, there's a lot of theories, and there's been
Right.
a lot of theories for a long time that have just really not been testable.
Right.
So
Is
I
any of
don't
this getting us in? It is helping us determine the neutron star?
Yeah, I think so. One of the things that LIGO can help determine, I think to a higher degree of accuracy, is the size of the neutron star. And I think
Okay.
one of the reasons that helps is in the different theories of, well, it gives us the sizes and the masses. So in the different
Right.
theories of these states of matter,
Right.
they'll give you different radii of the bodies for a certain mass.
Okay. Yeah.
So
I think
basically,
I would give you that. My brain can't handle the how that gives you what's inside.
oh yeah, I'm not really sure either, but you at least can set some kind of boundaries, where it's like if your model gives you a larger mass than
Yeah.
what's seen, then
Well,
it doesn't work.
the larger the mass, the smaller the actual radii on those.
Is that true?
It crushes itself even more. Is what I'd seen.
That could be true. It's been a little bit since I've gone into.
I just got into this thing trying to figure that one out. So I did a little bit of Wikipedia research, that's all.
Okay.
So, yeah.
Well, then I'll take
But
your word for it.
thanks for that. I appreciated that.
Yeah, yeah.
Little piece of information.
Could that, going back to Jerry's question, that restorative force, the fact that you have a gravitational field, doesn't that affect and make an electromagnetic field? Because gravity, all that's interrelated, electromagnetism and so
I don't.
maybe the gravitational field actually creates some kind of electromagnetic field, and that dissipation of energy is that restorative force, why it's not continuing. Because they're
I don't
all
know
tied
that.
together, electricity, magnetism, and gravity. And a magnetic field is perpendicular to an electric field, just the way this gravitational field is perpendicular,
Mhm.
when it goes out. So maybe it has something to do with it generates an electromagnetic field, and that's where that other energy is to cause that restorative force to stop.
Mhm. As far as I know, gravitational waves don't create an electromagnetic field, though maybe that's a part of GR that I didn't get the chance to get into.
Yeah, it's accelerating charges that create an electromagnetic field or a wave. And here it's accelerating mass that causes a gravitational wave.
Yeah, and them being fundamental forces, I think means that you can actually have these separate waves from these forces because they are independent of each other. So I honestly can't tell you that much about the restorative force. Unfortunately, I wish I could, but
well, thank you.
but I enjoy all these theories. It's very interesting, and it's just these types of questions that that will stump you when you go into these talks. So I'm definitely gonna write down some slides, do a little research, and hopefully have some better answers. I'll fix that math error too. That's very important.
Could you
Very
quickly
much, Yannick. It was great. It was a great presentation.
Thanks.
could you quickly go to that slide that had the graveyard?
Yeah.
So this is showing the different signals of the different mergers that you've detected so far, correct?
That's correct.
It seems very symmetrical down the vertical center. What is that about?
That's a very good thing to notice. It was an artistic, stylistic choice by the person who created this plot. So it's just they took all of the mergers and they decided they look best if you basically, I think they probably aligned it along, lowest mass on the outsides to highest mass in the center. Just to give a nice representation. So the x-axis doesn't really represent anything concrete.
Okay.
Yeah.
Okay.
But I think there are other ones like this that are, I think, chronological, like from left to right.
Yeah.
But in this case, it's just, I think they just chose to show it this way because they thought it looked nice.
Okay.
Yannick, I have one other question. You talked a lot about the duties of as an operator, maintaining the laser and keeping it its beam together. I was curious, what frequency is the laser, and is it ever varied, or have you folks found that a specific frequency gives you the best results?
That's a great question. I cannot remember off the top of my head what the frequency of the laser is. I think I get it kind of muddled because the photon calibrator that I worked on as a technician had a different frequency, and I don't want to just say one off the top of my head because it'll probably be that one.
Okay.
As for determining which frequency to use, I'd have to think about what went into that. My guess is that it would have maybe more to do with trying to keep the frequency of the laser as like the frequency bandwidth as narrow as possible. I don't know how much it has to do with the actual frequency relative to the gravitational wave signals that are coming in. I think because it's so well constrained, you could probably subtract it out pretty easily from the final detector signal. But that's another great question that that I'll have to make some more slides for.
Amazingly precise piece of equipment, though, to be able
It
to.
is.
Yeah.
It's crazy. There's I didn't get a chance to mention this, but like there was someone who would go on runs along the arms during their lunch break, and that's like things that you can detect.
Oh, no.
And like there's this base level of seismic noise that microseism that can cause us problems, and it gets really high if there's storms off the Alaskan coast. So just like the higher waves, you know, the stronger waves hitting the coast creates this this noise floor that ends up causing a lot of problems, especially in the winter when the ground is harder, because the waves travel more easily. So like it's a very, very sensitive detector. And then the Livingston one has its own problems because the ground is like jello because of the swamps. So they have a hard time with earthquakes because it really moves the ground a lot.
Nico, when Tim asked about the frequency, there's a possible good slide for you to add to it, because I was going to ask about, you were talking about trying to keep it within, and I was wondering how many nanometers you're keeping it within, you know, back and forth. I mean, are we talking 4 nanometers? Are we talking 40 nanometers?
Oh, that's a very good question.
So I don't worry about it now. I'm just saying that would be an interesting thing to see, is how many nanometers this thing is operating at theoretically.
Yeah.
And pluses and minuses you're trying to keep it into.
Mm-hmm. I think there is some component of general noise in the detector that you can't avoid. So like they are trying to keep them within these very strict distances from each other, but they also record the positions of the servos, so that if there is some kind of small movements, you can subtract that out later. So
you said the actual wavelength of the laser is slightly lower and higher.
sorry, I definitely misinterpreted that.
No, we're
yes.
not talking length of the detector. We're talking about the actual wavelength of the frequency of the laser, having to keep it in such a tight parameter. And I was just curious how tight
what is the like the bandwidth and whatnot. I'll add another slide for that. That's a great question.
Yeah, I was just once again, really good presentation.
Thank you.
Just one other question. You had mentioned that because of the polarization of the gravitational wave, that it may not be detected at an individual station. It comes in at, say, 45-degree incidence to the arms. Do you have any estimate of overall what percentage of gravitational wave signals are not, or mergers are not being detected because of that?
I don't. I mean, it's I guess a mix of things, because the different detectors are all at slightly different angles from each other, right? So if one gravitational wave signal is perfectly out of polarization with one detector, it's going to be at least slightly in polarization with another detector. So after that, the real questions are which detectors are online at the time. And, you know, if all 3 of them are, you probably should see something, but it also depends on the strength of the signal. So the further off this ideal polarization axis it is, the weaker the signal is going to be. So you have to take into account all of these things, like how strong was the signal originally, and then now that it's tilted, you know, now how strong is it going to show up in the detector? Is that something that's detectable by LIGO? And so I don't actually have a number. I don't know if it's very well. Again, it depends how many of the observatories are running. If all 3 are running, it's probably pretty low. And as we get more, you know, the one in Japan, the one that's going to be built in India, that kind of an issue hopefully shouldn't be too much of a problem, because there'll hopefully always be at least 3 detectors up and running.
Okay, thank you.
Has anyone studied when you have a gravitational wave and you have such a small distortion in space-time, what it actually does to like matter or energy in that change? Like what effect does it have?
I don't know. I think at the amount that it's affecting us, they're extremely small, like I said.
Well, not for
thousands of-
human, but for like an atom or
Like if you had like a larger
an
wave
elementary
or
particle
something.
or something, yeah. But
I don't know. I think that in terms of theory, there might be some ideas. In terms of concrete examples, we just now are able to tell if a gravitational wave is actually present or passing through, and it's at very low levels. So I don't think there's, I don't really know about.
anyone studied that?
Yeah,
Maybe that'll be down the road.
It's ripples in space-time. So I think that, like, say an atom sitting in space that has a gravitational wave that passes through it, as far as I know, is not really going to be affected, but it might be worth asking someone else about this as well.
Since one of the black hole mergers compressed the Milky Way by the width of a thumb, I don't know how you can translate that down into the size of an atom. That'd be below a Planck's measurement, wouldn't it?
Well, the arms of LIGO, don't they change distance less than the
Less than a
in a
proton.
nucleus, in an atomic nucleus?
That's correct.
Yeah, so
Or-
very little interaction. I mean, occurs.
Once again, I think we're getting into smaller than a Planck's length
Right.
at the atomic scale.
Mhm. Yeah, so in terms of I guess I'm not really sure if it's maybe if it was a very strong wave and you were close, there might be some noticeable effect. But as far as I know, it doesn't have too much effect on matter besides passing through and causing these distortions. I think there's an old Star Trek episode where they're really close to merging bodies that might be black holes or neutron stars, and the gravitational waves make them all like really drunk, and so they
I think I
can't
remember
operate
that
the
one.
ship.
Yeah.
Oh, no.
But that's probably not accurate, unfortunately.
Had nothing to do with that bottle of tequila.
It was Klingon juice.
Well, thank you very, very much, Nico. It was a wonderful presentation, and we've done our job at preparing you for your thesis defense.
Yeah, thank you.
Thank you again for coming out tonight. We really appreciate your talk.
Thank you. It was great giving the talk. You gave me a lot of questions that I'll have to inform myself a bit better on, and I appreciate that. So thanks a lot.
Very good.
So Nico, if something else comes up interesting and so forth, and you develop another talk like this, can you contact us? We can always love to hear from you again.
Sure. Yeah.
Yeah.
I'm
Drop us a
sure.
line if you got something new.
Yeah, there was a lot of jumping around. There's a ton to talk about. So even with the current stuff, I'm sure if I do a little research, I can find some cool new developments.
Yeah. We'd love to hear from you again.
All right. Sounds good.
All right.
Thank you very much.
Thank you for an enjoyable evening.
No problem. Right back at you. All right. Have a good night.
You
Good night.
too.
All right, Michael, back over to you.
Unmute yourself. There you go.
Okay, now we're mutual. Okay. Now that was a lot of fun. I said Yannick instead of Yannick. I should know better. The Murdoch murder mysteries, which I just happen to love. I don't know if any of you have seen those or not, but the star is Yannick Bisson. And I just should have caught it. But anyway, whatever. It's definitely a Canadian name, I believe, or French Canadian. Anyway, let's see, Doug, did you want to just kind of give a little lowdown on maybe what happened this last Saturday with the photographer with?
Okay, so actually everybody can keep an eye out for a free advertising magazine at certain, and I should have contacted the editor and found out where you can get this. I will email everybody, but I need to get this magazine is called 209. Once again, it's just a free magazine. They put it in different advertisers' locations that you can pick up. And they sent me a few questions that I responded to by email. And then they sent a photographer out to our June 4th Astronomy in the Park. Unfortunately, all we can see were nebulas that were sitting about, a few thousand feet above us. So it was a solid cloudy night. Couldn't even see the moon except for about 20 seconds. But the write-up and some pictures will be in this magazine. And once again, I've got to contact Nora and find out where we can find these magazines and so forth. And I'll get that information to you guys. Next Astronomy in the Park is on July 9, Saturday, July 9. I will not be there. I need to have somebody else the key so they can be the last one out and lock the gates. I'm going to be up at the cabin in Strawberry. And then as thank you, Tim.
I've got the.
You got
date
July
wrong there.
8th? Wait a minute,
I've
double
got
check.
the-
Double check. Let's see here.
Saturday's the 9th. I got the wrong date. It's
Okay,
the-
okay. Good. We got that there. So it is Saturday the 9th. Yeah, and then like I said, August 6th will be the next one. And then August 13th, we have a public outreach grow for the Girl Scouts. It's a full moon. We'll need a couple of scopes out there. Maybe we could do something in the day with the solar filter, the solar telescope. She was going to get back to me on that. And I don't know exactly where we're going to set up on that one. So if you would like to help out on that one, you just keep in contact with me. And like I said, we'll go out there and do that. And that's basically it for the public stuff.
All right, thank you, Doug. Okay, I would like to make an announcement, and that is Jerry's been our benefactor forever. And he's really the man responsible for us having our meetings over there at UOP, and also having a Zoom account through the University of Pacific for us to have these meetings. But unfortunately for us, and very fortunately for Jerry, that he's retired. And so it won't be long. We won't have access to the this free Zoom account, right, Jerry?
That is correct.
Okay, so in our Constitution, I think anything over $100, we need to get an approval from the members. And so I think in the next newsletter, it should be published in there. It's not terribly expensive. You know roughly what it would be for that, Jerry?
I think it was $150 for a license, Eric. Is that what you said last time?
Yeah, the going rate is an annual subscription for $150. That's correct. I think the first year there is some special promotions that happen. So the first year we'll probably be able to get for a cheaper price, but I would just think of it as a flat $150 rate every
Actually,
year.
when we do that, though, we're going to have to make sure we don't, when we budget it every year, we're going to have to know, because it's going to go up and up as long as they can get more money out of it. So
In time, it might go up. Yes.
yeah, it will go up in time. So,
But regardless, that's a pretty fair price.
yeah,
Without these Zoom meetings, I mean, our board meetings, we could probably have. We'd be eating a lot of pizza, I guess, and that's really not good. And secondly, as far as the actual meetings that we're having like tonight, that would be non-existent until we actually have a place to have these meetings. And with COVID still being up in the air, I mean, it seems to be a new variation every 6 months or 3 months. So I think we really need to have this. This has been a very, although maybe not the best way, the old way was better, but we don't have that choice. So I think everyone should be aware of this. On our next Astronomy Club meeting next month, I would like to go ahead and have a vote. We need a quorum to pass this. I think it's 10. So we should have, I hope, at least 10 people attending. Please have more. Just be aware of this, and I will call for it. And I hope you all understand, but this is really important that we need to do this. Any questions? You can ask Jerry or myself or just about anybody on the board. We pretty much know the same thing. I think probably the most knowledgeable one would be Eric.
Even if COVID were to go away, this is still a very positive thing for being
Yes.
able to get speakers from Antarctica.
Yeah.
And,
Yes.
and British Columbia. So yeah, we can get so many more speaker opportunities with if we can keep Zoom going one way or the other.
And I didn't mention is if we do have a place to have meetings, we still need to Zoom because like Jerry says, this is really invaluable. A few years ago, it seemed kind of ridiculous, but boy, was that prophetic when Fred said that we should actually get involved in Zoom. It was a new method of communicating, but he was spot on and we've used it very effectively. So I'm hoping that you'll approve this. If not, I'm just going to have to strong arm everybody to chip in $10, I guess. So you don't want to do that because we have money on that. Okay. So we good on that? All right.
Just real quick, just so everybody is aware, we are looking for a physical location to meet at, and we are currently exploring the idea of meeting at the Nature Center at Oak Grove Park. The biggest hurdle there is trying to get a internet signal strong enough and not strong enough, but
Wide enough bandwidth.
that won't drop, so that we can have these Zoom meetings. So if anybody already has like a 5G phone and is already receiving a 5G signal, maybe you could help out and go over to the Nature Center and just see if you are getting a good signal in the area, or if you know somebody that does. I don't personally know anybody that has a 5G phone, but me and Doug went to the Nature Center for our last EC meeting and kind of did a test on 4G, and it worked, but it was complaining about the signal not being very steady. So yeah, if you just have anybody that you know of that has a 5G phone, let me know. We can work out a test. Or if you guys know of another place other than the Nature Center that we could potentially meet, also let us know. We'll investigate that as a possibility.
Potentially free.
Yeah.
Actually, let me expand a little bit on what Eric was talking about. So the problem with the internet connection at the Nature Center is there is not an actual physical cable into the Nature Center. It is done by a hotspot, which is basically like your phone receiving its internet via the airway. And there's a cell tower not far away, but unfortunately, the bandwidth, the components that are in that cell tower are not working, and they're not getting upgraded and so forth. So the signal, my Verizon signal was not very good. I could not get mine up and running. The AT&T signal that the Nature Center itself pays for, the docents at Oak Grove pay for, was doing well enough where Eric and I could be at the meeting, but when we tried to show a video from Eric's laptop, it wouldn't take it. So right now, it doesn't seem like we're going to be able to do it at the Nature Center until we can get a better internet connection, more bandwidth, and the hardwired cable or fiber optic, actually, to talk about, is a year or two away. So that's where we're at on this thing for the Nature Center.
All right. Board members, any other topics or any announcements that need to be made that we may not have mentioned earlier?
Yeah, Mike, if I could, you saw this slide a minute ago and Doug went through all the public events. You also see the June, July, and August star parties here. they're also published. The one I wanted to point out to everyone is this save the date item here at the bottom of our plans for September 24th, high altitude star party and potluck. That's always a lot of fun. And if you put a mark on your calendar, we're going to try to go up to the heliport like we have traditionally done. My wife has told me she's not going to cook that night, so I want to make sure that y'all are going to bring some food on September 24th, okay?
Not for you.
Not going to Peddler Hill, Tim?
Yeah, Peddler Hill, isn't it?
What did I say?
You said Hilliport.
I meant Peddler Hill. It was first priority, yeah.
Okay.
Yeah, we'll know more exactly.
Yeah, and just to mention as well, don't mean to be Debbie Downer, but the last 2 years, Jeff and I have been going up to the high altitude as often as we could, and we did not get one observing day up there, and that's simply because of all the fires that have been up there. So this could be a fly in the ointment again. I hope not. I would love to be able to go up and all this have a good time.
Yeah,
But
hope
if
you're
that
gonna
does
be
happen,
around.
we're gonna have to make adjustments.
Did anyone make it up to Peddler recently since I've been up there with the tree across the trail and everything, the road?
No.
No.
No?
Well, I'll just have to bring the chainsaws with us, Bill.
Yeah, or chain it up and drag it out, one of the two.
How big was it?
It wasn't that big. I would say it was about a 16-inch DBH. So, maybe about a
I got a 20-inch
70-foot tall.
I got a
Yeah,
20-inch
it'll
bar, so
cut
I
it.
can handle it.
Yeah,
So we
Is
can
there a
always-
back door?
yeah.
Yeah, there is. But we can open the front door.
Oh, okay.
Yeah. Not a
I wanted to ask Doug about the Girl Scouts event. You mentioned solar. I have a solar telescope.
Okay,
Are you planning on doing stuff in the day for solar? Because
well, that's
I
what.
was a Girl Scout and I'd like to help out.
All right, definitely. The thing is that right now, the plans are still nebulous, okay? But that was one of the things I tossed out there. And so she's supposed to get back to me whether we're gonna be doing, they don't call it merit badges, they call it something else. But yeah, definitely put that on your calendar.
So let me
and-
know. Yeah.
Well, like I said, I will definitely do that. Tell you what, Dina, send me an email again so that I can update your information.
Okay.
Give me your cell phone number and everything again. So that way we can,
I don't know if I have your email. Do I just use this email from this club?
yeah, you can do that. But let me give it to you right now. Let me just give it to you right now.
Okay.
Are you ready?
Yeah, go ahead.
Space Cadet Doug, no spaces, all lowercase, at
Space Cadet
gmail.com.
Doug.
Space Cadet Doug.
Yeah.
My brother came up with that one and I like it.
Okay. At what though?
What's that?
Space Cadet Doug at
Gmail.com.
Gmail. Okay.
Yeah, go ahead and send me an email, and like I said, and I will keep
Okay.
you in on that one. Because yeah, we don't want just a bunch of old fat white bald guys,
Hey, come on now.
Well, you're not
I'm
fat.
not that old.
We have to show girls that women can do it strong.
That's right. That's
That's
right.
it.
Absolutely.
Bob, the reflector came out. Did you get your copy?
No, I have not. It's supposed to come in the mail?
Yep.
No,
Nope,
email.
it's email.
Email? I haven't seen it in the email either.
Okay, it came out several days ago.
I got mine.
I got mine.
I got
email.
mine.
I got my hard copy.
Yeah, me
Oh.
too.
How'd you do that?
Well, if you ask.
I
for a
get hard copies.
Yeah,
Yeah.
You have to be
Okay, I'll
hard-headed.
look into
Have to be
that, Bob.
hard-headed.
I will keep looking.
Well, I'll send you a copy of it, but they must not have updated the address from the last club roll call I sent. I've sent another one soon anyway. It's time to renew. So, but,
Okay, thanks. I appreciate it.
okay.
Well, until they send him his copy, make sure you reduce our club count membership by one.
Oh, yeah. Really?
Yeah, it charges.
Yeah, do it by 2 because Mark's not getting his either.
Right, right.
Yeah, in fact, I got it right there.
Oh, yeah. Beautiful.
All right, ladies, gentlemen, anything else? Looks like we covered a lot of topics tonight. Had a great speaker.
We have.
Very good meeting.
All right.
Nothing for me.
I will bid you all a good night.
All
Have
right.
a good evening.
Good night.
Thank you all.
All
I
right.
appreciate
Good
your
night, everybody.
attendance.
Good night. Thanks for a great meeting.
Bye.
Yeah. All be
Bye.
safe, please. Take care. Okay, I'm going to close the meeting then.
All right.
Good night, everyone.
Night.
Good night.
All right.
All right.
This is where we find out who is asleep.